I'd like to start off with just some simple motivations. I think everyone on this call, and by the way, we have a wide audience of maybe 20% professors and maybe 60% or so decision analysis, decision quality practitioners, and then maybe 20% are golfers, ranging from enthusiastic amateurs to mental coaches to swing coaches and teaching professionals. So welcome to all of you. I think one thing we all share in common is an interest in decision quality, making the best decisions we can for situations that involve more than one variable at a time being uncertain. And that certainly would be true for many decisions, anything involving targets. Today, we're going to work on golf shot aimpoint, but in business, portfolio resource allocation, allocating resources across a basket of market security or real estate assets, oil fields, R&D portfolios, businesses. Multivariate uncertainties are everywhere, but the fact is that they're rarely used. And the reason they're rare, multivariate probability distributions are rarely used in practice is that they're too hard to use. So frequently, they're not used, and we end up sacrificing decision quality. In golf, interest in decision quality, and that term has not really yet emerged in golf, but the idea of aim better, score getter, or make better decisions as to what to practice and so forth, these ideas are rapidly emerging, and multivariate distributions, as I'm going to show, can help achieve that. I've been wanting personally as a golfer for 50 years to do an analysis such as the one that I'm going to be presenting today, and it has not been possible. There are recent advances in technology, both on the golf side and the decision analysis side, that have made possible what I'm going to be presenting today. On the decision analysis side, it's the emergence of quantile parameterized distributions, which started in 2010. And then there are papers in 2016, 2017, 2019. And this is a rapidly emerging field, but it gives us the intuitive ability to parameterize probability distributions more easily than we have before. The second major innovation is the strokes gain system, introduced in a book by Mark Brody called Every Shot Counts in 2014. Mark Brody is a Columbia Business School professor who applied dynamic programming to golf and ended up developing a far superior measurement system that allows golfers to measure the quality of their golf shot versus their peer group compared to just how are they doing relative to against the golf course. These two innovations together have allowed me to put together this introductory webinar. And as you can see at the bottom there, I've got a preprint paper which is just published as of a couple of days ago. Please feel free to download it, and any comments are, of course, welcome. So here we're going to introduce three new approaches for decision analysis. Two of them are methods for creating and using multivariate probability distributions. And one of them, the first one, will be what I call the marginal conditional metalogs. It's based on the definition of conditional probability, where you can decompose any multivariate probability distribution into a marginal and a set of conditionals. The second is Metalog copulas, and that's based on another fundamental decomposition that I'll explain shortly. And by the way, there could be a lot of technical content in this presentation. I'm going to go relatively light on the technical content because I do understand that there's a wide range of technical skills and capabilities and background on this call. And so if you want the full mathematical detail of how all of this works out, please go ahead and consult the preprint paper that I mentioned. But the other new aspect is application of decision analysis to strategic decision making in golf. It's not really been applied much in golf before, but I think based on what I know, now is the time. The idea here is aim better, score better, without any change in a player's swing or physical capabilities. And also what we're talking about here is pre-round strategy and building your intuition to make better decisions on the golf course. The idea is play better, play faster, and it's certainly not paralysis by analysis on the course. And in fact, what we're doing here should enable you to make decisions more quickly on the course. I'm going to use as an example the fourth hole at the Stanford University golf course. This is the Google Earth view of the hole on the left. It's about 160 yards, par 3. When the pin is tucked on the right corner of the green, as you see here, it's very close to a treacherous water hazard called San Francisco Creek. And the question is, where do you best aim your golf shot? And in the close-up of the green on the right, you could aim at the hole. Some people would advocate that. It's always better to be aggressive. You could aim at the fat part of the green that's farther away from the water hazard. You could aim short and left of the green, but then you've got a chip shot. There are a wide variety of choices there. Tom Weiskopf in his book would have said, be aggressive, go for the flag. He's a former touring professional. Jack Nicklaus would have a more nuanced view, and we can talk about that as we go. The important thing to realize about choosing an aim point is that you're not just aiming one shot at one point. In fact, wherever you aim, there is a shot dispersion pattern associated with that aim point that a golfer does not have control of, except to the extent that they can improve their skill level. As Stanford's coach Conrad Ray said to me recently, the secret sauce is the choice of aim point is more like aiming a shotgun than a rifle. Nowadays, I think most touring pros and many top amateurs, when they look at a hole and think about their next shot, they actually have in mind the whole shot dispersion pattern and picking an aim point with respect to aiming that shot dispersion pattern, the center of it, in the best possible place. But this is a concept, interesting, that most amateurs I know are not even aware of yet. It's all so new. The golf technology, based on Brody's book, is emerging extremely rapidly at this point. And these kinds of analyses are part of what can ultimately come out of it. So let's move on. I've just mentioned 3 possible aim points, but obviously the complete set of alternatives here is a continuum in 2 dimensions. You could aim at any of these blue circles, and the question is, what's the best one to aim at? Now, based on Mark Brody's book, and he analyzed more than 10 million shots that have been kept track of by the PGA Tour for every touring pro, every tournament, every shot, where it started, where it ended up, expected strokes to get to the target, and so forth. Data has been being collected since the early 2000s. That allows us to map every golf course in terms of the expected number of strokes to hole out for a given peer group from any location. So, for example, if the hole is right here on the right front of the green, if your ball is 8 feet from the pole, it turns out that good golfers make about half their 8-footers. They miss about half their 8-footers. 1.5 is the number of expected strokes to hole out from there. If you're farther away, like 32 feet, good golfers mostly 2-putt, but they 3-putt from there about as often as they 1-putt. So 2.0 is the expected strokes to hole out. The water hazard over here, 3.5, that's a bad place to be. The bunker is bad, but not as bad, and so forth. You can look at the various points. Every square yard here has an expected strokes to hole out number associated with it. I'm not going to go into further detail on that for this presentation, but for these purposes, I'm going to keep this map. I'm going to take this map as given. Now, how do we calculate the value of an aim point? Well, golfers are interested in making as low as possible their strokes on a hole. And the question is, when you hit your first shot from 160 yards away, let's say you aim it at this aim point right down here, front and left, but what you're really aiming is your shot dispersion pattern. And you could end up with any one of these shots within this pattern, even some outside this 95% confidence ellipse here. But if you want to quantify the value of the aim point, you simply look at the expected strokes to hole out for every one of these blue dot shot pattern points, and average across them. Now, this assumes risk-averse behavior, or I'm sorry, risk-neutral behavior, which is, of course, reasonable given that there are many hundreds of shots that take place over the course of a golf tournament. Anyway, for this particular location, the expected strokes to hole out from that point is 2.4. The question is, what's the best aim point in any of this area here that would cause that number to be lower, indeed, if there is such an aim point that would cause it to be lower. So you say, well, how would I know anything about my shot pattern? Well, it turns out that shot pattern data is pretty readily available. When I was a kid growing up, I used to watch Gene Littler. He would go out to an empty athletic field and he would hit a lot of shots with a 6-iron or a lot of shots with a driver, and he actually go and try to learn something from his shot dispersion pattern. You can measure it directly. But again, within the last 5 years, there's a lot of technology available to help. In most anywhere in the golfing world, most metropolitan areas, you can go to a so-called top tracer range. And here, just a couple of months ago in Seattle, are some shots, 40 shots that I hit with a 9-iron. And it will come back and tell you exactly where did you hit each ball. And so you can calculate or estimate your own shot dispersion pattern from that. This is just a cell phone photograph of the TV monitor displayed there after I was done. There are also sensory recording devices where you can put sensors on your golf clubs. Your cell phone is connected to GPS. They can figure out how, the apps can figure out how far did you hit every shot. This whole area of golf technology is evolving extremely rapidly at this point. And then, of course, there's peer group data collection. The patterns I'm going to be using here are for touring pros or top amateurs like Division I college players, but we'll do sensitivities later to see how that would change depending on your assumption. So if we know some things about shot dispersion pattern. There are a lot of things that various shot dispersion that all shot dispersion patterns have in common. First of all, the farther away from you are, or the longer the shot is, the wider is the dispersion pattern. That's not surprising. But secondly, due to the physics of golf, there are certain facets that almost all shot dispersion patterns would reveal. One of them is that there's a correlation between hitting the ball left and hitting it too long. There's a correlation between hitting the ball short and hitting it right. That's because if you're a right-handed player, a shot to the right typically happens because your club face is open relative to its path at impact, and that adds loft to the club, which causes the ball to go shorter and spin to the right and stop more quickly. It's just the opposite for left. Typically, the club face is closed relative to the target line. It creates hook spin, which causes the ball to roll further, and also takes loft off the club to cause it to go further. So most any shot pattern for a right-handed player like that would look like something like this. It would be tilted. And for a left-handed player, it would just be the mirror image opposite. There's also an asymmetry involved, and that is that shots that are short, that there are many, many more ways as a golfer to hit a ball that ends up being short of the target than long. Rarely do you hit a shot that's so good that it goes 5 or 10 yards past the target. Usually it would just go a couple of yards past the target if you hit it really well, particularly off the fairway. But there are lots of ways you can hit a relatively poor shot that ends up being short of the hole. So there's a skewness here. A given distance significantly short is more likely than a given distance significantly long. So in whatever we do to capture shot dispersion patterns, we need to capture these particular characteristics. Now, turn now to how can we create a probability distribution over the two variables, distance and direction, that will appropriately capture these kinds of characteristics of shot dispersion patterns. According to the definition of conditional probability, we need a marginal distribution, let's say over direction, and then a conditional distribution over distance given direction, and that will characterize the whole shot dispersion pattern. Let's start with the marginal distribution over direction. For this is just simply, I'm going to use simply a Metalog distribution, and I'm going to just do a very quick review of what the Metalog distribution is for those of you that may not be familiar. Metalog is short for metalogistic. Here is the equation, x as a function of probability y of the logistic distribution. The Metalog is simply a series expansion that gives you lots of shape flexibility of these mu and s parameters of the logistic distribution. And like a Taylor series, a Metalog distribution can have any number of terms. You can see here everything from 2-term Metalogs to 10-term Metalogs. Note that in this equation, there are a set of A coefficients. I'll say how to get these A coefficients in a moment from your data. But note that this entire equation is linear, whether you have 2 terms or 10 terms in these A coefficients, and that's an important property. Basically, every time you add an additional term, you add capability for more shape flexibility. By the time you get to 8 or 10 terms, you've probably got more shape flexibility than you'd ever need. This equation, just for those of you with a technical background, is easily differentiable. And what that means is, once you have this quantile function, the inverse CDF shown here, it's easy to differentiate and see the corresponding bell-shaped curve, which could be skewed or have any shape really at all. But those two things are available in closed form. Now, let's talk about where do we get the A coefficients from. And I'm going to start with the golf example. Let's say that for a good golfer, and I think this is true for many good golfers, something in this range, that about if you're doing the best you can to hit a golf shot from 160 yards, maybe about 80% of your shots would end up within this range of 10 yards right of the target and 10 yards left. Maybe one shot in 10 would go farther left than 10 yards. One shot in 10 would go farther right than 10 yards. And I think for most good players, by the time they get to that level, you could say right and left are equally likely. That's not true for most amateurs, but let's say the center of this tree, the median, equally likely to be either left or right. Well, that simple assessment gives rise to, given the linearity of all this, what you see on the right, 3 equations and 3 unknowns. Basically, this simple assessment here are these 3 points on the curve. You've got 3 equations, 3 unknowns. You simply solve those with a little bit of matrix algebra, and you get this simple equation here that is the exact formula for this curve you're seeing shown right here. And there's the bell-shaped curve. This one turns out to be a logistic distribution exactly, which is the Metalog for only 2 terms. But as far as I can tell, that's actually pretty reasonable for most good golfers, or for many good golfers. And if it turns out you're more expert, then you could shrink this range. This also could be skewed. It doesn't really matter. I'm just going to use this simple symmetrical example to get started with. Also, with Metalogs and actually quantile parameterized distributions more generally, according to the 2011 paper, if you have more data, if you have lots of data, then you can just always fit a Metalog or a QPD to it with ordinary least squares. So that, again, that's a simple closed form calculation. So here are the key features of these quantile parameterized distributions, which I say are a recent innovation that's made this analysis possible. First, they're parameterized by quantiles, which are easy to interpret, and that's extremely important. Secondly, QPDs over the last 10 years, and mostly over the last 5 years, have been emerging as distributions of choice for practical application. I know of at least a dozen businesses, ranging from consulting firms to Fortune 500 companies, that use QPDs primarily instead of classical distributions, except in special case circumstances where you needed those distributions. By now, there are more than 100 literature citations to QPD since 2010, and interestingly, most of those are applications. You can see down at the bottom that the earlier papers tend to have more literature citations than the later ones, and that's, of course, not at all surprising. Metalog distributions, which are a subset of QPDs, have some additional properties. One is virtually unlimited shape flexibility. We now have a theorem that says any continuous quantile function can be approximated arbitrarily closely by a Metalog. I've mentioned these next two. With Metalogs, there's a complete choice of boundedness. They can be unbounded, semi-bounded, or bounded. We're going to use the unbounded today because that's what makes the most sense for this example. There are some limitations that we actually don't come close to running into today, but if you'd like to read about them, you are welcome to do so. So let's now talk about what is really the heart of the matter here. How do we develop the conditional distribution over distance, given that you have this marginal distribution over direction? Let's turn right now to that. Now, one way to think about that is to actually look at the shot dispersion patterns that I showed. But as I mentioned, let's just assume for the moment that you've hit a shot that's exactly on target. It's going straight at the target. What's the probability distribution now over how far long or short it might be? Well, what I mentioned before is that a given significantly short is more likely than significantly long. So I've put in here 80% chance that you'll go within this range from 3 yards short, from 5 yards short to 3 yards long, 10% chance of being longer than 3 yards long, and 10% chance of being shorter than 5 yards short. Again, that's pretty reasonable. This tends to have a narrower range in terms of yards than the direction. And so, yeah, I think, this is a pretty good place to start. Now, what about, however, suppose you had the information that the shot is actually 10 yards right. Well, that would cause me as a golfer to believe that my probability distribution is now, the whole thing is moved more toward the shorter side. So what you can see that I've done here is I've simply subtracted 2 yards, and I've got the same 1090 range here, but the whole distribution has shifted a couple of yards because, given the information that my first shot is 10 yards short. You would do the same thing, something similar, if the first shot is 10 yards left. And basically what I've given now is a rule for conditioning the quantile parameters of distance based on the outcome of direction. And that rule is simply, as stated here, the median distance increases by 2 yards for each 10 yards of direction left. The 1090 range differences remain constant. If you go through those equations that I just showed, it leads to a very simple Metalog equation for this probability distribution, which now depends on x1, the result of direction. If you have, and that's the important characteristic of it. You need to know the result of direction in order to have your probability distribution over distance. And you can see here the corresponding curves to this equation, which have exactly characteristics that I just mentioned. If you hit the ball left, it tends to be farther, and so forth. So let's now let's talk about what we've just done. What we have just done is we have effectively parameterized this entire shot dispersion pattern with 9 points off of this tree. And you can see the 9 points that are right there. This means that parameterizing a multivariate QPD is as easy as doing a conditional probability tree of the kind we would use in decision analysis all the time. And it's really just these 9 points with the relationship that I've put that connects them for in-between points that parameterizes the whole shot pattern. Critically and importantly, these control points, these assessed points, or points that are determined from data, can be moved around in any way you want. You could take this point, move it up here, take this and move it down here. You could take these and move them closer together. Actually, any rule whatsoever, it doesn't have to be linear, as I just showed, any rule whatsoever can be used to condition the parameters of distance as a function of direction. Once you have this, it's very easy to simulate. If you just pick a random sample from a uniform distribution, which is a Y1, you plug it into this equation, you get your sample for direction. If you pick if you pick a random sample from a uniform distribution, plug it into this equation. And by the way, I don't know if I said on the previous graph, yeah, this is the equation that results from this simple rule assumption. And so you just plug Y2 into this equation, you get your simulated value, and that's what gives you this entire shot pattern. The nice thing about this is you can parameterize the shot pattern to be tailored to whatever happens to be your specific golf game or your specific peer group. The resulting joint probability distribution can be plotted in 2 dimensions. It's like a 2-dimensional bell-shaped curve, which has all the desirable characteristics we just mentioned. Also, any multivariate probability distribution has implied distributions that typically do not have an explicit functional form. Well, with the metalogs, those can be fairly easy to get. For example, we have the marginal distribution over distance, but we don't have, over direction, but we don't have the marginal distribution over distance. But to get that, we can just line up all the results, the yellow dots, from the simulation over distance and direction. And here I've just lined up the distance dots, and we can easily fit a 3-term metalog to that, and you can see it's a very accurate fit. However, if it weren't a very accurate fit, in another case, you could use a 4-term or a 5-term metalog. With adding terms, you'd certainly get enough flexibility to capture most anything. This corresponds to the curve that has the skew short capabilities or situation that we mentioned. Now we'll turn to the nub of the matter here. What is the best aimpoint? And what I'd like you to do is, just for our interest, enter into the chat what you think is the best aimpoint based on everything I've said so far, and the choices, and just put A, B, C, or D in the chat, and we'll accumulate some of these results and see what they have said. A is aiming directly at the hole. B is aiming at the fat part of the green, where you would have a longer putt, but are less likely to go into the hazard. C is aiming just short and left of the green. And D is aiming just left of the hole. Why don't you quickly, I'll give you 15 seconds or so to put whatever you might think would be the best aim point in the chat. And just to clarify again, I'm talking about where you're aiming the center of your shot dispersion pattern. That would be the median on both dimensions, understanding that you've got a shot dispersion pattern that you may be visualizing around that. Okay, well, let's proceed. It turns out that the best aim point here is point D, 3 yards left, 1 yard long of the target. That's interesting because one would think that one might think that one of the other more conservative plays would be better, or you might think that playing aggressive, such as right at the hole, would be better, but actually it's not. If you look at the information I'm displaying on the right here, aiming at this point D with the center of your shot dispersion pattern is about 2 strokes better on average per 18-hole round than aiming at the hole or at either of these other locations. Most golf tournaments are won or lost by far less than 2 strokes around. This is with no change in physical capability. So this is just thinking better, aiming better. The reason for this, by the way, is for a good golfer, you give up too many birdie opportunities if you aim up here or down here. You're in the hazard too much if you aim directly at the hole. It's better to bias your aim a little bit left of the hole where you can still make a lot of birdies. All of this can be done easily in an Excel spreadsheet, as you can see here. All these equations are so simple. The whole multivariate distribution analysis can be boiled down to a simple data table here that shows the difference between aiming at the hole and aiming anywhere else, such as this at this point D in terms of expected strokes to hole out. Before I leave this slide, let's take a look and see how the result of this analysis, the best aim point being D, compares with the intuition of the people participating in this webinar. Specifically, many of you provided in the chat your intuitive estimate of the best aim point by voting either for A, B, C, or D. The result of those votes is as follows. About 41% of you voted in favor of B being the best aim point, that is the fat part of the green. The second most popular is actually what I believe is the correct answer, D. About a third of you voted for D. About 20% voted for C, just short and left of the green, and just a few of you voted for A, aiming directly at the hole. This is interesting in the sense that for about 2/3 of the participants on this call, the analysis would presumably help aid your intuition by helping you make a better decision toward D, in contrast to what you would have thought otherwise based on intuition was the best aim point. I had one of the older golfers who was one of my peers on the golf team at Stanford say to me the other day, well, I don't think in terms of these aim point patterns, but I think I bias my aim point instinctively a bit. And of course, that based on years and years of experience, a golfer learns to do that. But what we're talking about here is how to learn to do that, in a webinar or with some additional thought. So let's now turn to the second method here. In 1959, mathematician Abe Sklar produced a very interesting theorem which said that any joint probability distribution can be decomposed into a set of marginal distributions and a copula that couples the marginal, and that copula contains all the relevance and dependence relationships. To keep this simple, I'm simply going to use the two marginal distributions that we just derived using method A and focus a little bit here on the copula. So using a copula is very simple. The bigger challenge is choosing or finding the correct copula. But to use a copula, and I'm not really going to go through the probability integral transform here, but the bottom line is if you sample from a copula, you can sample correlated samples from a uniform distribution, then you plug those into your marginal distribution as shown here, and you get samples of distance and direction, your two variables. It's very, very easy to use if you can get these random samples from your copula, and you can simulate a whole shot dispersion pattern that way. The challenge is picking a copula, and there are a number of classical copulas out there. If you're not familiar with them and you want to learn something about them at a high level, you could look at the Wikipedia article on copulas. These graphs are taken from that article. They go by, this is a bivariate student T copula here, and what they're doing is they're plotting the Y1 and the Y2 on the unit square, and you can see the student T copula is correlated in all four corners. Well, that's not probably right for our example. We've got a so-called Clayton copula here that looks almost like a shotgun pattern going out. Well, I don't know. How would the problem is, how do you pick a copula? Now, there are various analytical methods to do it. But in this case, I just wanted to try to be as illustrative and simple as I can, and went ahead and derived the copula that corresponds to the method A analysis we just did. And here it is, the correlation left long, short right, you can see here. And really you end up gauging, well, what copula looks, unless you've derived your own copula, which many people do in financial industries, particularly quantitative finance. But if you haven't derived your own copula and you're picking among the classical ones, you end up with almost this hunt and peck method of saying, well, what copula does my distribution look like? And that's a lot of guesswork. But overall, this one may look mostly like the bivariate Gaussian copula, except that you have to reverse the corners here, which can be done with a negative correlation coefficient that approximates it. And if I did that, and I had to cheat a little bit, and I took the shot dispersion pattern and calculated the correlation coefficient associated with that. But if I do that and plug it into the Gaussian copula, I really get, with these orange dots, a shot dispersion pattern that's really very much like the shot dispersion I had from using method A. They're really very similar. And I wouldn't be able to, looking at this as both a golfer and a probabilist, I wouldn't be able to tell you that one of these is a lot better than the other. So the copula, by the way, is guaranteed to honor the exact marginal distributions, including this short long skewness that we've discussed. So the question is, how would that affect your choice of aim point? And the answer, interestingly enough, is if you used method B, the copula method, you'd end up with almost exactly the same aim point. In fact, it's only 1 yard difference. So my conclusion from all this is that you basically, if you already know of a copula that you trust and believe in, and it's easy to get the marginal distributions, then you might as well use method B. If you don't, the marginal conditional metalogs, where you parameterize the rules or use the rules to come up with your conditional parameters, might be a better option. But in any case, you would get a similar answer. Now let's go on and do some sensitivity analyses. I'm going to do methodological sensitivities, where these are of interest to decision professionals that have to do with what method did we use, and then I'm going to do some golfing sensitivities that have to do with golfing skill levels. So let's go on to the second methodological sensitivity. What if instead of using the whole shot pattern, many decision analysts would ordinarily gravitate toward assigning 25, 50, 20 probabilities to each of these branches, and then just using that 9-branch pattern to come up with the best aim point. And that does work well for many problems. It does not work at all well for this problem. In fact, it would give you the wrong answer. It would give you the answer that would say the best aim point is directly at the hole. And that aim point, as we know, is 2 strokes worse than aiming at the best location for an 18-hole round. Why does it get you the wrong answer? Well, first of all, none of these points are in the bunker, so you have 0 probability of going into the bunker, but also 25% of them, 50% times 50%, are both on target, distance-wise and directional-wise, which means you've got a 25% of getting a hole-in-one. Well, that, of course, is ridiculous. Chance of a hole-in-one is, even for a skilled golfer, is less than 1 in 1,000, maybe even 1 in 10,000. So that method would not be a good method to use for this application. Another question is, well, what if we just, why do we need all these QPDs, even though they're easier to use? Why shouldn't we just use a traditional distribution like the multivariate normal distribution? Well, I plugged one in and I use the same means and variances and so forth as in MESA and the same correlation coefficient. But the multivariate normal distribution produces a somewhat different answer. It's not a terribly different answer, but it's not a very good answer. And the bottom line is, not only is it not as good an answer, it's also not as an authentic representation, because the normal distribution multivariate normal incorrectly assumes that a given distance long is equally likely as the same distance short. So it's both harder to use and not as accurate. Might as well not use it. Might as well use what we have just presented here. Now let's go to some golf sensitivities. These are important from a golf perspective. What I have here is the base case 1090 range plus or minus 10 yards. What if you were a better golfer than that, plus or minus 5 yards? I don't know that there are any golfers in the world, actually, that could hit 80% of their shots from 160 yards within plus or minus 5 yards. Maybe there are a few pros at the top of their game, but this would be an extreme situation where somebody is actually that good. If you were that good, however, the best aim point would move. You'd just be 1 yard left to the target instead of 3 yards left to the target, because you get more birdies that way, and you've got very few shots that are going to go into the hazard. What if you're a less skilled golfer? What if your 1090 range is plus or minus 15 yards? Well, in that case, you need to buy it. Your best aim point is to target where you're aiming farther from the hazard. And in this case, it turns out to be about 6 yards from the hazard instead of 3. What if, now this is a pretty wild golfer, this is a high handicapper. What if your shot dispersion pattern is such that 10% of your shots go farther right than 20 yards and 10% of your shots go farther left than 20 yards? If that's the case, your best aim point is over here, short left of the green. So the bottom line is, with greater shot dispersion, you would play more conservatively with respect to the hazard. I would note that wet and dry course conditions can reduce or increase shot dispersion. So it's not just a matter of golfer skill level. And also golfer skill level, with less skill, you'd probably have higher expected strokes to hole out. These results would not change if the higher expected strokes to hole out from every location is proportional. But if you were a terrible bunker player, for example, and you're here in this group, and you're a terrible bunker player and you frequently blade shots out of the bunker into the hazard, well, then of course you'd want to aim farther away from the bunker. So down here might actually be your best choice. So this all gets tailored to a golfer's skill level. Are there situations where you should play more conservatively? The answer is yes, and this is where you would take risk aversion into account. And the golfers here will know what I'm talking about. But if you're playing match play, where only winning, tying, or losing the hole counts and not your absolute score, and your opponent hits his or her first shot into the hazard, and now it's your turn to tee off, well, your aim point is likely, your best aim point is likely to be more conservative and aim short and left of the green, leaving yourself an easy choice, because that way you'll both maximize your probability of winning the hole, given that your opponent's already in the hazard, and minimize your probability of losing it. So risk aversion can indeed come into play. Another question might be, well, what if the pin, instead of being on the front right, is on the back left of the green? Well, the back left of the green is far enough away from the hazard and the bunker that at that point you might as well aim directly at the hole. So, and that's true for a very wide range of shot dispersion patterns. It's not nearly dependent on golfer skill level as is the best aim point when the pin is on the front right. Okay, so in terms of conclusions, just say a couple of summarizing things here before we go to questions and answers. We've introduced practical methods for constructing and validating multivariate probability distributions using QPDs, 2 methods. We've introduced a novel approach using decision analysis to determining golf aim point strategy. The whole idea is aim better, score better, which looks like it'd be 2+ strokes per round, according to the quantification I've done. No improvement in physical capability required. What are the ultimate goals here? One of my ultimate goals in doing this research is to make shape flexible, continuous, multivariate probability distributions easy and effective to use in practice. As I said at the beginning, most people don't use them. They've just been too hard. Now we can just parameterize them with these intuitive 9 points, or it could be 16 points, or however many points you want. But with the intuitive, easy parameterization and simple equations, they should be easy to use. And the second thing we're trying to do is provide golfers with insights to enhance their performance and enjoyment of the game. We hope this research will be viewed as a positive contribution to both. There are a number of resources available. If you download this presentation, any of these links here are clickable. There's excellent opportunities to learn more about Metalog distributions and indeed QPDs more broadly. There are multiple books that deal with golf strategies besides Mark Brody's groundbreaking book. And as I say, the whole world of this is moving extremely rapidly with apps that are available on your phone, online coaching. Ones that I found to be particularly useful are Decade Golf, Imagine Golf, and Top Speed Golf. These are all excellent according to your interest. So with that, I would like to close the presentation. A warm thank you to all of you professors, practitioners, and golfers and golf coaches and golf teachers out there. Thank you for joining me in this webinar. And what I'd like to now do is turn it back over to our moderator, Jay Anderson, for the question and answer period.
Tom, a fascinating talk. Enjoyed every bit of it. Boy, do we have lots of questions. So I'll keep the slides up there because a lot of these questions are specific to the slides, and I'll try to guide you to the questions, the slides that were the questions were asked about. So first, if you go to page 8 in your deck.
Page what, Jay?
8. Page 8.
Okay.
We got a question about, yeah, right
there it is.
That's it. Okay. So relating to this slide right here, should one look at the variance as well as the expected number of strokes? So you've got the expected number of strokes there. What about the variability?
That's a great question. The answer is, if you are a risk neutral golfer, that is, that you would make your choices according to the expected or probability weighted strokes to hole out, then no, you should not include the variance, because on average, you will do better if you use the probability weighted strokes to hole out over a lot of shots, like a couple of hundred that you would have in a tournament. Having said that, you would take the variance into account if you're risk averse. And that was the last example I showed with the match play. But for most golfers in most situations, 95% or more, using the expected number of strokes to hole out is probably the best metric.
Okay, thanks. Let's go to slide 20 now.
Okay, slide 20.
Yep. And this.
Here we go.
Yeah, and that one right there, where you got your 9 points there. So the question is, could this be used to fit a Metalog to errors of actuals versus a forecast, as in any forecast for any outcome or aim point?
Yes, I would certainly think so. I don't see any reason why not. I mean, what we're talking about here, the golf dispersion patterns are basically errors, right, relative to an aim point. I don't see any reason why this could not be extended to be used to look at and consider forecasting errors when actual information becomes available. I haven't thought about it carefully, but conceptually it would seem to make good sense.
Okay, now let's back up a slide to 19.
Okay.
And in this conditional distribution, Tom, I see that what you've got here is regardless of whether you're 10 yards right on target or 10 yards left, the dispersion you've got on the X2 variable is the same. So the question is, does it need to be the same, or can you be tighter to the right than you are to the left, for example?
That's really a great question. That obviously comes from a knowledgeable golfer. The answer is yes. The answer is no, it does not need to be the same dispersion. If you wanted, you could say, okay, when I'm 10 yards right, it's 0 to -5, which would be less dispersion. When I'm 10 yards left, it's 8 to -6 or something like that. Absolutely. And in fact, I even thought about making the example that way, and I just didn't do it for reasons of, wanting to make this equation as simple as possible. But absolutely, all of that detail can be put in there. And in fact, as I mentioned, you can move these points around wherever you want, and the multivariate metalogs will just adjust themselves accordingly. You just need to specify the rule that, according to which that behavior occurs. That's all.
Okay. Here's an interesting question from OJ, and I was actually thinking about this myself, Tom. How do you adjust the aim point for weather conditions?
Okay.
Playing on a blustery day.
Okay, let's go back to this this last here. There are a couple of ways. One is if the weather conditions are wet or dry. If the course is very wet, a ball is likely not to bounce and roll. It just lands where it does and sticks right there. In that case, that basically reduces the size of your shot dispersion pattern. Not this much, not as much as I'm showing here, but it basically reduces a little bit. If the course is very hard and dry, it increases your shot dispersion pattern because the ball hits and rolls. So that's one way you would take it into account. The other way is, suppose there's a strong wind blowing. Suppose there's wind that's blowing 15 miles an hour from, let's say, left to right. Well, that's going to be blowing your shot strongly toward the hazard while it's in the air. Well, in that case, naturally, and of course, you would want to adjust your aim point farther left of the hole to take into account how much the wind might move your shot.
Okay. So here's an interesting question from Brian. On the example you gave us, you got a par 3. But let's say you're on a par 4 instead, and you're on the tee. And as you're thinking about your shot dispersion for your tee shot, should you also be thinking about the subsequent shot dispersion?
Absolutely. Absolutely. It's a great question. And yes, this whole theory extends all the way back to all expanded drive. You're standing on the tee, and let's say you're standing on the tee on a par 4 hole, and there's a water hazard on the right and it's relatively open on the left. Well, what you need to do is aim far enough left so that maybe only one chance in 20 would a ball go into the water hazard or out of bounds. For me personally, as a golfer, I would aim in that situation, maybe 35 yards left of the hazard, if the hazard's on the right. Other golfers might aim 40 yards left. Others might aim 20, depending on what their skill level is. Probably even most pros would aim more farther to the left than 20 yards. But the key, according to Mark Brody's book here, is that you can, with your shot dispersion pattern for a driver, you can do exactly the same analysis. You can put it out there 250 yards, 300 yards, wherever you hit your driver, and you can move it around, and you can calculate the best aim point based on expected strokes to hole out from wherever that driver shot ends up. And golf courses can be mapped in terms of expected strokes to hole out for the whole landing area of drives. And in fact, they have been mapped for that. And your strokes gained, according to Mark Brody, this brilliant way of measuring is expected strokes from where you teed off, which might be on a par 4 hole, maybe it's a 4.2, okay, expected strokes to hole out, minus the expected strokes to hole out from wherever you end up. So maybe you ended up in a place where you're 3 strokes to hole out, minus 1 for your shot gives you a 0.2, if I did that math right, strokes gained on the field by hitting the drive into a particularly good location. But anyway, yes, the answer is this whole analysis applies to driving, to second shots, to layup shots on a par 5, because the whole courses can be mapped in this way, and golf dispersion patterns can be understood and modeled, as I've shown.
Okay. Here's an interesting question, maybe from an economist. You were talking about risk aversion and stuff. What if you weren't risk neutral about the number of strokes, but you were risk neutral about purse money?
That's a really great question. Prize money is heavily weighted toward the winner. The second and third place finishers don't get nearly as much, and then it declines rapidly from there. So it's very nonlinear. If one is risk neutral on prize money, then that would imply non-risk neutral behavior, I believe, in strokes, particularly coming down to the last few holes. For example, the leader could rightfully be slightly risk averse with respect to strokes over the last few holes. I just play a bit more conservatively. Similarly, a competitor who's just a stroke or 2 off the lead could rightfully be slightly risk preferring in strokes over the last few holes. I haven't really done that analysis, but I think it would likely come out that way. And as I say, it's a great and insightful question.
Okay, so we're almost at the top of the hour. So before I turn it over from Hilda, I'm just going to ask one more question that came in. It's kind of a cheeky one, Tom. Has your game improved since you started doing this?
That's a great question. Yes, it has actually. It's improved significantly since I've been learning all this, and I find it. I obviously don't have all this stuff memorized when I tee off on every hole, but after you've done a few of these analyses, you get an intuition, and I actually just visualize my shot dispersion pattern when I'm standing up to the ball and think about where do I aim that given this situation. There's no doubt that that's helped me. My handicap's down at least 2 strokes.
Great. Well, thank you again, Tom, and I'll turn it over to Hilda to close things out.
Well, what a fun presentation. I'm not even a golfer and I loved it. Thank you, Tom, and thanks, Jay, for moderating. Ladies and gentlemen, this concludes today's presentation. Again, I want to thank our presenters and you or your attendees for your contribution to today's event. I want to remind you that all our webinars are posted on the STP website in the library section. Thank you for being with us today, and you may now disconnect.